Our team is designing a rapid response aerosol dispersal crowd control hexacopter in order to fill a need in the police department's arsenal that could respond quickly to de-escalate situations.
The current limitations for our sprayer project is there's no current design for this purpose. Specifically, there is agricultural drones that use the same concept, but they use a pump instead, and the only other alternative would be a 40mm grenade launcher attached to the bottom of a drone, which would launch tear gas grenades, but these have a low coverage area, as well as sending dangerous projectiles into massive crowds. Our solution would have a greater coverage area. It would have no ammunition because it's an aerosol form, and it would involve less human interaction. Using this decision matrix, we have split off the scoring system into 5 major points: weight, coverage, refill time, pricing, and battery requirements. And each one of those is given a score, and with those scores, they are all rated at level of importance. So you multiplied that by the relative importance, and you get a score out of 10. Out of this, we decided that the CO2 system was the best possible system for this. Because of the simplified design, the CO2 has less weight, which allows us to have more storage for the material or the liquid that we'll be using to disperse. Pump systems are more reliable and they don't have an additional refill time, but because of this, they do have more weight, which allows for less coverage area. So using this information, the CO2 is the best possible decision. Using the CO2 design, we will run a 20-ounce CO2 canister. These are typically used in paintball guns. This will then run to a solenoid valve, which we'll be able to control remotely. This will then run through a 2-liter bottle, which will contain our pepper spray or tear gas liquid. And then from there, it will run to a rail system and then to our nozzles. Most nozzles are rated to be working efficiently at our max efficiency at 65 psi, and most 2-liter bottles are rated to be tested at 200 psi. For our prototyping, I was thinking that using the 2-liter bottle would be the best possible option because it is lighter than most of the tanks that I found. For the future for the sprayer, this summer we'll work to finalize the part selection and then acquire the materials. And then in the fall, we'll assemble the design and then run all the tests, such as which nozzles work the best and different spray patterns to be most efficient in these types of situations at certain heights. We'll analyze the data from these tests, and we'll use that to finish.
We gotta ask ourselves, how many propellers? We often see drones with 6 or even 8 blades and automatically think that having more motors is better, but that isn't necessarily the case. A hexacopter can reach higher altitudes than a quadcopter and also travel faster. Since hexacopters are more expensive, though, they're usually used for transporting more precious cargo which cannot survive in a crash. They are also much larger than quadcopters and more difficult to assemble and store. For our intents and purposes, the stability of a quadcopter will be plenty, and we won't need high efficiencies for spraying purposes. With this in mind, we would ideally want an octocopter because of the increased thrust and stability, which would be monumentally beneficial for our purposes of carrying around a heavy payload full of sprayer fluid. Much like the photo here of the DJI Agris. Due to our budget constraints and goal to reduce costs, we will be using a hexacopter frame, which will result in a maximum performance to cost ratio. The aerospace analysis consisted of determining what size propeller would be appropriate. An increase in propeller diameter may reduce the cruise RPM for the same cruise speed, but will also increase the load on the engine and therefore increase the fuel usage needed. In effect, you may reduce the cruise RPM, but you burn the same amount of fuel and you increase the stress on the engine. To maximize the efficiency, we must use the largest propeller possible. The new constraint is now the size of the drone frame, which will determine the propeller we can use. This is found by taking the smallest of the length or width of the drone and dividing by 2. The propellers then need to be slightly smaller to provide rotation clearance between the adjacent propellers. It's in our best interest to select the largest propeller that will fit onto the drone frame. The frame is now the constraint, as it now gives the maximum potential size for a propeller. And given our budget restraints, Shad will now go into the details of our hexacopter specs.
Alright, now on to parts and features. We'll be using the M2213, which is 20 amps to 30 amps or equivalent motor. It costs around $50. We were also looking at the Luminous LU8, which has better weight distribution but costs a little bit and costs more, and it weighs a little bit heavier, and for that reason we're not choosing it, because if we have Luminous LU8, we'll also need a more powerful battery, which would increase the overall weight. So for this motor, the MT2213 can lift up to 360 grams, which is roughly around 30 pounds. So as seen in the previous slides, the sprayer falls between that range. We'll also be using the Mini 122 TVL as our front-facing camera, which has greater horizontal range, thus increasing our view, and the 360 fly, which will be underneath to observe the situation in a 360-degree motion. For the battery, we're using Ovnik 2 packs 11.1 volt, which has enough power for those motors. As of the moment, our budget is $175, so it falls between the $700 of budget that we got. As seen in this graph, our throttle power and motor power increases almost proportionally when using that 11.1 volts. For now, our efficiency for the battery looks good. Last but not least, we need some arbitrary dimensions for our drone.
The ratio between propeller distance HA and propeller diameter D, greater the ratio, greater the amount of thrust by the equation J equals HA over D.
And some parameters for the blade are given as well. This can change at any moment. But for now, we use the equation Q equals half rho V square. The Q stands for dynamic pressure, which is needed for the propeller because we're considering it's functioning at an air density. We're also having a function for the piston engine power, performance power with FP, and the thrust of F of P. Then we use the equation V equals square root of 2 times P of that time minus P divided by P to get our velocity. And also in our graph, you can observe that I put 11 revolutions per minute against the voltage that you're using for the battery, which is the 11.1 volt. And so far, our graphs looks good and our velocity looks good, but probably in the future, we can change some different dimension, try some different length to make it better.